second. Rate of flow of liquid. Rate of flow of liquid. That means volume of liquid flowing out per second. According to law of continuity, if A is the area of the orifice, easily can write A into V, where V is the velocity of a flux. That A into root of 2GH gives you the volume of the liquid flowing out per second through the given orifice. And another relation here is, suppose if we have two orifices at two different levels for a given container. If it is H1 from the free surface of the liquid to the first orifice, the depth is H1, and the other is H2, the height of the orifice, second one from the bottom, the range may become equal. R1 is equal to R2 possible if H1 is equal to H2. The depth of the orifice from the top surface of the liquid is equal to height of the second orifice from the base. If they are same, then the range will become same. R1, R2. Volume of liquid can be compared according to the relation of V1, V1. Or range, if you want, V1T. Suppose here the velocity is V1 and time taken may be T1. Here it is V2 and time taken may be T2. I can write V1 T1 equal to V2 T2. The range is same. This is important one. Immediately you can land to the answer if the question is of that type. Or if they ask the range, one they may give confusing you that the given H1, what may be from the bottom, the height of the orifice required to give the same range. Nothing but same. You have to write the answer H1 equal to H2. So the lastly is about time taken to empty the tank. Suppose at the base you have the orifice that may used to empty the tank if it is of height h, and base area is A2, orifice area is, then time taken to empty the tank T is equal to A1 by A2 into root of 2H upon G. I already told A1 is the area of the orifice, A2 is the area of the tank, base area of the tank, H is the height of the liquid column in the tank, G is acceleration due to gravity. That gives you the time taken to empty the tank. Another is, one of the applications of Bernoulli, lastly I take as a Venturi meter, which is used to measure the rate of flow of liquid with the different sections considered. Suppose if we have a constriction at some point and there are two vertical capillary lines having cross-section area, here A1, here maybe A2. The liquid rising here or in this, there is a difference of height h. So the velocity of flow is at what first section is V1, at this second section is V2. Then volume of liquid flowing out per second, even considering pressure at 1 and pressure at 2, and rho is the density of the liquid. Volume is equal to, already velocity of flow we have taken as 2gh, root 2gh into A1 A2 by root of A1 square minus A2 square, where A1 and A2 are the cross-section area of the Venturi meter tube. H is the difference in height of the liquid levels in the two capillaries. G is acceleration due to gravity. GH can be replaced because we know pressure is equal to rho GH. If you want a GH, P P by rho. P by rho is a pressure difference. I write here that pressure difference V is equal to square root of 2 into P1 minus P2 by rho into A1 A2 by root of A1 square minus A2 square. That Venturi meter where we can find the flow of liquid by taking the different size of the flow in horizontal level. So it gives you volume of liquid depends on the pressure difference between the two ends, A1, A2, area of the cross section of the tips. With the questions again I say that in all these, whether it is a time of flow or velocity of efflux, volume of flow, law of continuity, Bernoulli's theorem, or on this rate of flow of liquid through capillary tube of different construction is appeared and chance of appearing in NEET examination. All these relations are very important in hydrodynamics. We go to the fourth unit to see the synopsis about the viscous force or viscosity. In motion, we come across with the two units. The one is called fluid dynamics and other is fluid viscosity. In fluid dynamics, we started with streamline flow and turbulent flow, but all our studies depends on only streamline flow. We are not accounting the turbulent flow at all. Streamline flow and a non-viscous liquid we considered here. And in streamline flow plausible when velocity of flow is very small compared to critical velocity and no disturbance in the path of flow. Then every liquid molecule flows in a particular line in the tube, which we call it as a line of flow. Group of lines we are calling it as a tube of flow. In this, when velocity is very small and very steady flow across any section, irrespective of the area of the cross section, the volume of liquid flowing out per second remains constant. That we call it as a law of continuity. V1 equal to V2. Area of cross section into velocity of flow is always a constant. AV is a constant. And coming to this, when liquid is in flowing, the second idea is about the energy that possesses and leading to Bernoulli's theorem. There are three types of energies: by virtue of motion, kinetic energy; by virtue of configuration or position, the potential energy; by virtue of pressure difference, which is responsible for the flow of liquid as a pressure energy. Sum total of all these three energies, kinetic energy, potential energy and pressure energy per unit mass, is always a constant, and this relation is widely used in getting some problems in it. Again, the applications are concerned, it may be blowing of roofs of huts or any tin sheds when high wind is blown, or made the convexity of the aeroplane wings to increase the pressure from the lower side to take off, or in landing also to decrease the speed to lift off the aeroplane. Or we are studying about Venturi meter, and even we come across with the vehicle driving care. And later on we come to the liquid when you taken in any container. So in the side walls, if you made a small hole, which we call it as orifice, the liquid comes out through that. What is the velocity of efflux, and what is the time taken by the liquid to reach the ground, and maximum distance at which it reaches the ground as a range? We have three different relations for this: velocity of efflux, time of flow and range, and what is the condition for maximum range. And further we come across with what is the volume of liquid flowing out per second, that is A into V. Suppose we take a Venturi meter, come across with the relation of different size tube and different levels in the capillary height, tube and liquid height. We got a relation for measuring the volume of liquid flowing out per second, either in terms of height or the pressure difference between the two tubes. And later we come across with, even in container, if there are two holes are provided, one from the height, another from the bottom, if the height depth of the orifice equal to height of the second orifice, then range becomes same. And if you made a hole at the base or bottom of the container, time taken to empty the liquid or empty the tank is given by one relation a1 by a2 into root 2g, 2h by g, where a1, a2 and h, what the parameters are explained. But this time taken to empty the tank, whether it is velocity of efflux or the range or volume of flow, law of continuity and Bernoulli's theorem. There are only 5 important relations here and problems concerned, either from law of continuity or from Bernoulli's theorem or from this velocity of efflux or time of flow or range or time taken to empty the tank. The questions are repeated over and over on this most important out of other sections. This hydrodynamics or fluid dynamics is. And small, the unit we left is the 4th one, that is about the viscosity, the viscous force. We can take it later. The fluid dynamics is about viscosity. Here we deal with viscous force, then coming to coefficient of viscosity related to low dense liquid. We deal about one viscous force as a Newton's formula. The second is about the Poisson's formula. Coming to high dense liquid, we take the terminal velocity, and lastly about Reynolds number, which decides the nature of flow of liquid. The major part relies with all these. Every part has some relations and the numerical problems are coming from this. Majorly on Poisson's formula, terminal velocity and Stokes relation. We have to start with what viscous force is, then coming to viscosity, coefficient of viscosity. For any low dense liquid like water, what the Newton's formula, viscous force relation, and volume of liquid flowing out per second in horizontal streamline flow is given by Poisson's relation. And for high dense liquid, the idea of terminal velocity, how it is helping us to determine the viscous force using Stokes formula. And we have relation for terminal velocity also. Reynolds number is the many constants are merged into one and gives you the nature of flow of liquid, whether it is streamlined or turbulent, can be understood by that number called as a Reynolds number. We have to go one by one. For any liquid when flowing against on a surface, this is a rigid surface. When liquid is flowing, imagine like different layers having area of each. If you thought of area of each layer may be A, and separation between layers is dx. If v is velocity here, the upper layer may be v plus dv. Different layers even under horizontal streamline flow. As you come deeper and deeper into the liquid, normal to the flow direction, velocity of layers goes on decreases. So every layer is tending to pull back the other layers to move it forward. It has to move forward, therefore it pulls the other layers backward. Then a dragging force appears. And again, if you think top layer is only moving above A, when you take the lower layer on the other side to understand, that has to take the upper layer also. Its weight is more, the speed decreases. When you come to the still lower layer, it has to take the two other layers. As you come down and down and down into the liquid, the column of liquid flowing increases. That means it has to carry out the upper layers. Automatically its velocity goes on decreases. And here we measure or take the term as velocity gradient. Velocity gradient is nothing but variation of velocity perpendicular to the direction of velocity, the distance measured. The ratio, variation of velocity with respect to distance. Gradient, very word is variation of a physical quantity with the distance. That we learned in case of thermodynamics also, temperature gradient, where variation of temperature with distance. Even in electrostatics, potential gradient, variation of potential with distance. Similarly here, variation of velocity with distance is taken as velocity gradient. As it is directly, if you see, distance by time, only time remains, per second is SI unit. Dimensionally, if you go, it is only T power minus 1. And for low dense liquid, like water, we have studied about the friction in mechanics, solid friction, and between solid and solid. Friction is a dragging force, a resistive force which opposes the motion of any substance. Between two solids, it is called as a solid friction. You detail studied kinetic friction or static friction or rolling friction and all those, and you know the relations. But the second you have learned in the morning chapter about the force of buoyancy. It is also a frictional force between the solid and liquid, whether liquid is moving in solid or solid is moving in liquid. That also force of friction between a solid and liquid. Now another force, dragging force, now we come across different layers of the liquid. There is a dragging force, is again a friction. This is called as a fluid friction between two fluid layers. That fluid layers opposes one motion against the other. That we defined it as a viscous force. This viscous force is found to be directly proportional to area of each layer and directly proportional to the velocity gradient under streamline motion. Again I am saying, when we take the two together, we bring some constant A into dV by dx, where this is defined as coefficient of viscosity, a constancy brought for a given liquid. Viscous force depends on two factors: area of each layer of the liquid and velocity gradient, variation of velocity per unit distance measured perpendicular to flow. And constancy, that what we brought, is called as a coefficient of viscosity, which takes a role to understand the magnitude of the force. It depends on nature of the liquid. And this formula, nothing but called as a Newton's formula. So this coefficient of viscosity, we are defining and knowing its unit, and further on what factors it depends as to. Coefficient of viscosity. So it is measured usually in points. Or if you take coefficient of viscosity is equal to F into dx by dv. If you written in Newton, it is in meter per second. Newton per second is also the unit. It is a constant, but this coefficient of viscosity decreases with increase of temperature for liquids. In case of liquids, as temperature increases, no doubt like surface tension, coefficient of viscosity also goes on decreases. But for gases, increases with increase of temperature. If you take as general fluid, it may be both liquid and gas. In case of liquids, it is decreases with increase of temperature. Here it is directly. As temperature increases, coefficient of viscosity also increases, because gas molecules starts random motion and force of viscosity or viscous force goes on increases, and that leads to the concept of coefficient of viscosity. So with this, we go towards the Poiseuille's formula, volume of liquid flowing out per second.